If you keep peeking at the test set while tuning, the numbers look better on paper than they will in production. We will set up clean train, validation, and test splits in Python so you can stop overfitting your evaluation. You probably see optimistic metrics and wonder why a model fails in production. That is data snooping. I will show you how to separate data so your model tuning stays honest. You will learn a simple workflow that gives reliable validation feedback and a single, honest test score. I'm Professor Pi, teaching AI foundations from basics to advanced with simple, concepts-first Python that helps you solve bigger, real-world problems. Think about building a price predictor from sales history. You want a model that generalizes to new days, not one that memorizes past numbers. The split into train, validation, and test solves that. Train is where models learn. Validation is where we choose settings. Test is where we get a final, impartial score. At its core, the idea is simple. Hold out a chunk of data that you never touch until the very end. Use validation to pick model choices. Then measure once on the held-out test set to estimate real-world performance. The downside is you use less data to train, so later we often combine train and validation for the final fit. We will build a small pipeline that demonstrates this exact flow. First, we will create a reproducible split. Then we will fit a simple baseline and measure mean absolute error on validation. Next, we will try polynomial degrees and pick the best by validation error. After that, we will show threefold cross-validation on the training set as a steadier alternative. Finally, we will combine train and validation, refit, and report a single, honest test MAE. Now we create the splits. This snippet creates a reproducible train validation test split with a fixed seed. It starts by shuffling the dataset in a repeatable way, so every run gives the same partition. Then it slices into three groups: a training block, a validation block, and a final test block that we will never touch until the end. The key lines are the shuffle with a fixed seed and the proportions that allocate data into the three sets. The fixed seed makes experiments comparable and prevents accidental data leakage when you rerun or share results. Next, fit a simple baseline and check validation error. This snippet fits a simple linear baseline on train and evaluates MAE on validation. This fits a straight line model to the training data and then predicts on the validation set. MAE, mean absolute error, measures the average absolute difference between predictions and true targets and gives an intuitive error in the same units as the target. The snippet shows the model training call, the predict step, and the calculation of MAE on the validation split. That single validation MAE tells you whether the baseline is good enough before you try more complex models. Now we will search for a better polynomial degree. This snippet selects the polynomial degree that minimizes validation error. It loops over a small set of polynomial degrees, and for each one, it expands features and fits the same linear learner on the training split. For each degree, it computes validation MAE and records the result. The core idea is comparing models by their validation error, not by test error. The snippet highlights the degree loop, the feature expansion step, and the selection rule that picks the degree with the lowest validation MAE. Changing the set of degrees changes how flexible the models are, and therefore, how much they risk overfitting. Next, we add cross-validation inside the training block. This snippet uses threefold cross-validation on the training set for a steadier MAE. Instead of relying on a single training slice, it splits the training block into three folds, trains on two folds, and validates on the third, cycling through each fold. The snippet computes the average MAE across folds for a given setting, giving a more stable estimate of how that model behaves on unseen training-like data. Using three folds reduces variance in the error estimate, but costs more compute. If the average MAE is lower and stable, you gain confidence in the chosen hyperparameter. Now we refit and report a final test score. This snippet refits on train plus validation and reports a single honest test MAE. After choosing the best setting, it combines the original training and validation data into one larger training set and trains a final model. That final model is then evaluated exactly once on the held-out test set to produce a single unbiased MAE. The important part is the strict order. Choose settings using validation or cross-validation, then train on train plus validation, and finally, measure only on the test set. This final MAE is the closest estimate you have of production performance. In a real project, you would map the same steps to larger data. The split step becomes a time-based holdout for forecasting. Cross-validation may use more folds or a rolling window. The final refit on train plus validation gives you the largest model ready to deploy. Recap: split data into train, validation, and test to avoid data snooping. Use validation or cross-validation to choose model settings. One caveat: holding out data reduces training size, so validate carefully and refit on train plus validation before the final test. Next step, try increasing the polynomial degree range or add regularization, and compare validation MAE to see if flexibility or shrinkage improves real performance. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.